In this video here, we're going to take a look at the nearest neighbor algorithm to find an upper bound. Now, a couple of videos ago, we saw how we could find an upper bound for a network. However, the method demonstrated in that video can be difficult to use for large networks, as selecting shortcuts is difficult and time-consuming, especially when there are lots of vertices to consider. Now, there are other algorithms that we can use to help find an upper bound, and one of those is the nearest neighbor algorithm. And before we formally introduce the nearest neighbor algorithm here, the upper bound given by this algorithm always represents a possible tour. However, in general, it will not represent the optimal solution. So just so you're aware there, please do make a note of that. So before we work through a practice question together here, let's just formally introduce the nearest neighbor algorithm. So as we just mentioned, then let's just formally introduce the nearest neighbor algorithm. So for step one then, all we do here is we select each vertex in turn as a starting point. But just note here then, for exam questions, you will normally be told to start with specific vertices. And you only have to check all the vertices if you're specifically instructed to do so. But for time purposes in an exam, they're probably not going to ask you to do that. Now for step two, we then go to the nearest vertex which has not yet been visited. Step 3, we simply repeat step 2 until all the vertices have been visited and then return to the starting vertex using the shortest route. For step 4, once all the vertices have been used as the starting vertex, we then select the tour with the smallest length as the upper bound. Now just be very, very careful here then that you do not confuse the nearest neighbor algorithm with Prim's algorithm. They are very, very similar, but just notice then with the nearest neighbor algorithm, we look for the vertex nearest to the last vertex chosen. So it is an important distinction there. Please just be very, very careful. And with all that in mind then, let's just work through a practice question together here. So let's just get started then with this practice question here. Now, as we can see then for this question here, right, split into 3 different parts, A, B, and C. Now, parts A and B are concerned about applying the nearest neighbor algorithm. As we can see here, starting at different vertices. So for part A then, we start at B, and for part B, we start at C, if that makes sense. And then for part C here, it just says, hence revise, determine which value should be used as the upper bound. So quite a typical exam style question here. Normally there would be some context attached to the question. But for now, more than anything, I'm just concerned here that you can actually apply the nearest neighbor algorithm to find an upper bound. Okay, so let's just begin then with part A here, which I'm going to do in a different colored pen. Let's just do it in green here. So for part A then, let's just do this at the top here. So that's concerned with this matrix here. Now, they are just the same matrix here, and I've just done that just to make my life a little bit easier here with part B, but I'll explain that once I get to that part of the question. But for part A then, as it says here, right, all we want to do then is just apply the nearest neighbor algorithm, starting at B to the matrix below to find an upper bound to the traveling salesman problem. Now, if we're starting at B then, what I do here to begin with is put a 1 above column B, like so. We then delete the corresponding row here. So we delete row B, like so. And what I now do here is just look down column B, right? And what I want to do then is choose the smallest possible value, which corresponds to this 9 here. So we circle 9, like so. I then put a 2 above the corresponding vertex, which is D here. So we've gone from B to D. So put a 2 above D, or column D here. And again, we just delete this row, or the corresponding row. So I delete row D, okay? Now what I'm also going to do here, as I work through the nearest neighbor algorithm, is just make a note then of what vertices we traveled to. So I've gone from B to D here, okay? So we've gone from B to D, and that had a weight of 9, okay? So it had a weight of 9, like so. And at this point here, we just repeat this process, right? It's pretty straightforward for the most part. So what I do here is I look down column 2 only. Now, that is an important distinction here because this algorithm is very, very similar to Prim's algorithm. We did mention that in the introduction, so it is important that you don't get confused here between the nearest neighbor algorithm and Prim's algorithm, okay? The difference here then is with Prim's, I will look down both column 1 and column 2 and choose the smallest possible value. With the nearest neighbor algorithm, what I do here is look down column 2 only, right? So we look down the previously selected column only, if that makes sense. So looking down column 2 here, as we can see, then the smallest possible value is simply 10, right? So I put a circle around 10. That is from D to C, right? So I put a 3 here above C, and we also delete this row. Okay. What I'll also do here is make a note then that we've gone from D to C, right? So D to C, and that had a weight of 10. Perfect. Okay. Again, we just repeat this process, right? Now looking down column C here, or column 3, whichever you prefer. And what I can see here then is the smallest possible value is simply 6. So again, I just circle this like so. So what we've done here is gone from C to E, right? So I put a 4 above E, like so. And we also delete the corresponding row here, row E, like so. So we've gone from C to E here. So I'll also make a note of where we traveled. So C to E, and that had a weight of 6 here, okay? And at this point here, as we can see, then we're getting pretty close to the solution, right? There's not too much more to go here. So looking down at column E here, or column 4, as we can see then, we don't really have much of a choice, right? It's just simply 15. So I circle 15, like so. So what I've done here is gone from E to A, right? So above A then, I'll put a 5 here. I'll circle that and also delete the corresponding row, which is row A, okay? So I've gone from E to A here. So E to A, and that had a weight of 15. Perfect. So at this point here, as we can now see then, what I've done here is deleted the full table, right? Once you delete the full table, what that means here is we now need to just return to our starting vertex here, which in this case is B, as the question told us here. So starting at B, okay? So as you can see, I've kind of scribbled all over the table. So it's a little bit difficult to see underneath the table here, but looking at the original table underneath then, A to B here has a weight of 12. So all I'm doing here is just returning to our starting vertex. So A to B then has a weight of 12. So A to B then has a weight of 12. And therefore then for the upper bound here to the traveling salesman problem, that would just simply be the sum of all of these weights here. So therefore the length is equal to 9 plus 10 plus 6 plus 15 plus 12, right? So 9 plus 10 plus 6 plus 15 plus 12. Add those together. And what we get here then is 52, okay? As I mentioned before, there's no context attached to this, right? So I don't know whether this represents time or a distance. So I can't attach any units, right? So we just leave it as 52. Okay, so therefore then the upper bound here is 52. So the upper bound then is 52. Oops, I don't know why that cut off. 52. Perfect. Okay, so that gives us the solution there to part A. Now for part B then, as we can see here, it's pretty much identical. The only difference here is we now start at C as opposed to starting at B. So what I'll do here is I'll do this one in a different color. Let's do it in light blue here. So we're starting at C. Let's just highlight that here. So if we're starting at C, then all I do to begin with here is put a 1 above C, like so. Okay. So for part B then, starting at C here, I've numbered it, number 1, and I also delete the corresponding row, right? So delete row C. Okay, like so. Now looking down at column C here, we want to choose the smallest possible value, right? And in this case here, that gives us 6. So we circle 6. So what I've done here is gone from C to E, right? So I put a 2 above E, like so. And we also delete the corresponding row. So I delete row E. What I'll also do here is make a note then that to begin with here, we've gone from C to E. So C to E. And that had a weight of 6. Okay. And again, at this point here, we now just simply repeat this process. You know, it is very methodical, and hopefully you are finding this walkthrough here relatively straightforward. So looking down at column E here, again, what I want to do is choose the smallest possible value, which, as I can see here then, would simply be 12. Okay, so what I've done here is gone from E to D. Okay, and that had a weight of 12. So E to D. So E to D with a weight of 12. We put a 3 above column D, like so. And we also delete the corresponding row, like so. Okay. Now looking down column D here, as I can see then, the smallest possible value here is 9, right? So we circle 9, like so. We've gone from D to B here. So D to B, that had a weight of 9. So weight of 9 there. So what I do here is put a 4 above column B, and we also delete the corresponding row, like so. Perfect. Now, looking down column B here, as we can see then, again, we don't have much of a choice here, right? We just got the one choice of 12. So we just circle 12. Perfect. So what I've done here is gone from B to A, right? So B to A. Okay, so B to A, that has a weight of 12. What I now do is put a 5 above column A and also delete the corresponding row, like so. Perfect. Now, at this point here, as we can see then, similar to what we had in part A, right? What I've done here is deleted the full table. So, at this point here, what that means then is we now need to return to the starting vertex, which in this case here is C. We're starting at C, right? So, A to C then, what is the weight of that? So again, I've kind of scribbled all over the table. It isn't the neatest, but it doesn't really matter too much for the nearest neighbor algorithm. But as we can see then, A to C here has a weight of 10. Let me just quickly erase that just to double check here that I've not accidentally misread that. Yeah, so 10 there, perfect. Okay, so A to Z then has a weight of 10. And again, for the upper bound here, that would just simply be the sum of these weights here. So therefore the length is equal to, so it's 6 plus 12 plus 9 plus 12 plus 10. Add those together. Plus 9 plus 12 plus 10. What does that give us here? So add these together, and we should find that you get here then is 49. And again, there's no context that we can attach this, so we just leave it as 49. And in that case then, my upper bound here for part B is 49. So my upper bound here is 49. Okay, perfect. So that gives us the solution to part B. And then finally, for the very last part of this question here, part C, given that I've done part A and part B in different colors, I'm going to be consistent. I'll also use a different color here for part C. Just keep it in the same kind of fashion, right? You know, different colors. You don't have to. Just being a little bit special, but there we go. So for part C then, it says hence or otherwise determine which value should be used as the upper bound. And it does say that we do need to give a reason for our answer. So what I've got here is two different values for the upper bound, right? And that is the beauty of the nearest neighbor algorithm. So which do we choose here as our upper bound? So what I want to do here is choose the smallest possible value as the upper bound. And why is that the case? Well, if we choose the smallest possible value, what it does then is it reduces the interval containing the optimal solution, right? So in that case then, we choose 49 as the upper bound. So choose 49 as the upper bound. And what is the reason for that? Well, as we just mentioned then, it reduces the interval. It reduces the interval containing the optimal solution. Perfect. Okay. And there we have it then. I'll give that an exclamation mark. Perfect. And there we have it then. So as you can see, applying the nearest neighbor algorithm is pretty straightforward for the most part. I think the most kind of dangerous thing here with the nearest neighbor algorithm, once I can actually speak, is that you don't get it confused with Prim's algorithm. That is the real danger here with the nearest neighbor algorithm. But as long as you can remember the distinction here and the difference between those two different algorithms, you'll be absolutely fine. Okay. So there we have it then. That gives us the solution here to the one practice question for this video. And that brings us to the end then of this video here on the nearest neighbor algorithm to find an upper bound.